All right, so one last lesson on percents, and this is percent error. Percent error goes with percent of change very closely. So if you'll remember, percent of change that we talked about, amount of change over the original amount. Well, notice what the formula is for percent error. Very similar to that. It's the amount of error over not the original, but the actual amount. As you'll see, actual amount is very similar to original. The reason why we would find percent error is because we need to see, maybe we're doing a science experiment and it says this is what it should be, and then we do the experiment and this is what we get. We want to see how far off we are. And so by finding the percent error, we're able to say, okay, what's the actual amount? What should it have been? That's what's going to go on bottom. That's what we're comparing everything to. And so we'll still find the amount of error the same way by subtracting what happened minus what should have happened, and then dividing that by the actual amount, which is what should have happened. And so very similar to percent of change, like I mentioned. Couple of things dealing with percent error. Finding the percent error, like I said, is very similar. The actual amount, so what it should be, always goes on the bottom of your ratio. And then this one's important to note, the percent error will always be positive. And so in other words, there will also be no increase or decrease. In other words, if we are 25% off, we just say we're 25% off. We don't really, it doesn't really matter if we're 25% too big or 25% too small. We just care about what's the error that we are away from. And so this could be used maybe with estimation. How far off am I? How close am I to the number? It could be used, like I said, with experiments whenever we're trying to see how far off was I in my experiment versus what should have happened. And there's other ways that we can see what the percent error is. But I guess one example would be with like an experiment or a survey or a test with the coronavirus that we've been dealing with. If they're doing a study on something, if they're doing an experiment on maybe a drug to see if it helps, they're going to see, okay, how far off are we from what we want to be? And so they use percent error to see what should happen versus what actually happens whenever we tested this method, this testing formula, this vaccination, whatever it is. Okay, so let's look at some examples then. Ahmed wants to practice free throws. He estimates the distance from the free throw line to the hoop is 13.5 feet, but it's actually 15 feet. So find the percent error. So remember, this ratio for percent error is amount of error, and that is over or divided by the actual amount. Well, it tells us here what the actual amount is. It's actually 15 feet. And the way that we would find the amount of error is subtract those two, 15 minus 13.5. Remember, we always want this to be positive, so make sure it's bigger minus smaller, even if the numbers are switched in the question. When we subtract those two, we get 1.5 over 15. And then we go ahead and divide. 1.5 would go on the inside, 15 on the outside. And we put our decimal point straight ahead. 15 goes into 15 one time, and that's an easy division problem. So we get 0.1. Change this to a percent. Remember, 0.1 is not 1%. 0.1 would be 10%. So the answer is just 10%, and we don't have to say 10% increase or decrease. We just say he is 10% off. So that's what that means. He estimated it to be this. It was actually 15. He was 10% away. So let's look at another one together. Morgan estimates that it will take 12 minutes to download a movie from an online movie store. It actually took 15.5 minutes. We're going to find the percent error, and then remember what we did yesterday with percent of change, where we rounded it to a percent, and then, or we made it a percent, and then we rounded it to the nearest whole number. We'll do the same thing for this one. So in this case, once again, we want amount of error, and that's going to be over the actual amount. So the amount of error would be found by subtracting. So 15.5 minus 12. And that's going to be over what the actual amount was. It actually took 15.5 minutes. So over 15.5. 15 and a half minus 12 gives us 3.5 over 15.5. And then we go ahead and divide. So 3.5 is going to go on the inside and 15.5 on the outside. Now the decimal point is right here. We need to move it over one time to the right, which means we do the same thing there. So add a 0 and pull it up. 155 goes into 350 2 times. Oh, I'm sorry, the decimal point should be right here. Decimal point should be right there in between the 5 and the 0. It was 3.5, and then we moved it. Okay, so 155 goes into 350 2 times. So the 2 will go above the 0. 155 times 2 would be 310. Subtract that, we get 40 left over. We'll pull down a 0. Now, if it continues to go and we need to round to the nearest whole percent, like we did yesterday with percent of change, go to where there's 3 numbers after the decimal point. So we need to do at least 2 more times of division. It's going to be a 2 there. We subtract 310 again. We get 90. Pull down one more 0. And 155 goes into 900. It's going to go to 900 5 times. So we get 0.225. So whenever we go to round it, before we round, change this to a percent. This as a percent is 22.5%. And then we round it to the nearest whole number. 22.5 would become 23%. So from her estimation to what actually happened, she was 23% off. That's what we're saying. Not increase, not decrease, remember. It's just there was 23% error. So amount of error over actual amount, subtract on the top to find the amount of error, divide by what actually happened. Very similar to what we did yesterday with percent of change, and then round, change to a percent and round if you need to. So you all go ahead and do this last one on your own. If you need to pause the video for a few minutes, do that, and then we'll do it together and see what we get. All right, so the amount of error on top, and then our actual amount on bottom. Amount of error would be 13.5 minus 10. And that's going to be over the actual amount. And the actual amount would be 10. She is actually 10 whenever she weighs her. So whenever we subtract this, we get 13.5 minus 10, which would be 3.5 over 10. Okay, and then we'll go ahead and divide that. So 3.5 inside and 10 on the outside. 10 goes into 3.5 3 times, or sorry, 35 3 times. Subtract 30, and we'll be left with 5. Pull down a 0, 10 goes into 50 5 times. And so we're finished there. We get 0.35. And 0.35 would become 35%. So she is 35% off on her estimation. Okay, so that is percent error. Like I said, very similar to percent of change. And we've got 4 problems as well for today that you can work on that deals with percent error.